Hey, what's going on, guys? Welcome back to another stream here on the Math Studies LC channel. I hope you guys are doing well. So today, as may look from the title, we're gonna be studying the whole chemistry course. But right now, I'm kind of tired. So right now we're just gonna do like an hour. But in the morning when I wake up, we're gonna do 10 hours hopefully. Yeah. So without further ado, yeah. So if I come here, there's some options that my teacher did. I might just leave them out, I can't lie. But right now, what I really need to do, what I desperately need to do is I need to do the titrations. So what I'm going to do is I'm just going to open up volumetric. Yeah, I'm just going to open up volumetric here. I'm going to go here. I'm not going to give up, bro. I may be in a bad state right now, yeah, wallah, man. But I'm not gonna give up on this leaving cert, bro. The only way is up. When you're knocked down to the ground, bro, the only way is up, yeah? So I'm just gonna record myself. You guys can see everything. I'm using my wide lens so you guys can see everything. I'm not gonna get my course. There's not enough time. The anxiety that plagues our minds. It tricks our minds into doing no work. It tricks our minds into feeling like we're not good enough. Like, that voice has been in my head since, the last year or so, yeah? But I think it's time that I overcome that, yeah? And I truly achieve the potential that I am well capable of. And it starts here, and it starts today, and it starts now. Not tomorrow, not next week, not next month, not in the next 5 years. Today, now. Time is 8:49. Let's do this. So the first titration that we're going to talk about is, first of all, when we talk about titrations, the first titration I'm going to talk about is going to be the sodium. Sorry. Is going to be standardization of a HCl solution. So standardization of HCl solution using. So standardization. To standardize is to find the concentration of a solution by colorimetry or titration. And what is a standard solution? A solution of a known concentration. That's just some lingo, some terminology we need to know. Standardization of a HCl using. And guys, we're going to be doing similar streams for physics. We're going to be doing similar streams for maths. And we're going to be doing a bit of English every day as well. We're going to be covering one pod, hopefully, every single day. So yeah, so HCl is what we want to standardize, which means we want to find the concentration of this. But we know anhydrous sodium carbonate. That means we know the concentration of that. Okay, so we don't really need to know too much. Funnel, burette. So yeah, tip the contents of the clock glass into a beaker. Rinse the clock glass with deionized water. Pour the rinsings into the beaker. Using a clean, dry glass rod, we're going to stir the contents of the beaker as to ensure all of the solute dissolves. Then we're going to add a funnel to a volumetric flask, pour the contents of the beaker into the volumetric flask through the funnel, remove the funnel. Then we're going to rinse the beaker, the glass rod, and the funnel with deionized water. Pour those rinsings into the volumetric flask. Then we're going to add deionized water to the volumetric flask until 1 centimeter below the graduation mark. Then add dropwise until the bottom of the meniscus is on the graduation mark. Read at eye level. Stop and invert 20 to 30 times. Okay, so that's that. If it's a solution, we talked about a solid but if let's say it's a solution, right? So you wouldn't weigh it on a clock glass using a mass balance. Therefore, let's say the solution's in a beaker. We're going to get a pipette, yeah? And we're going to draw up the solution into our rinsed pipette using a pipette filler. And then we're going to then add it to a beaker, right? But we're going to ensure that we touch the tip of the pipette against the inside wall of the beaker as well. And we're going to draw it out slowly into our beaker, and then the rest of the steps are the same. Now, when we talk about burettes, guys, first of all, what we have to do is we have to rinse the burette. Now, when we rinse the burette, first of all, we have to talk about rinsing the burette. How do we rinse the burette? Like, how does that even work? So first of all, you're going to rinse the burette with deionized water to clean it. Then you're going to rinse it with the solution it is to contain, as to ensure that we do not change the concentration of that solution. Then if we take a pipette, no, burette, how do we fill it? So the way to fill a burette is very simple. Close the tap, add the funnel, clamp it vertically on a retor stand to avoid the error of parallax. We're going to add our solution until until like 1 centimeter above the zero graduation mark or above the zero graduation mark. Then place a waste beaker underneath the burette, open the tap, allow the solution out until the bottom of the meniscus is on the graduation mark, read at eye level. And like if you want to read at eye level, you can get up on a stool as well and look at eye level as well. Now for the pipette, again, how do you rinse it? We're going to rinse it with deionized water to clean it, rinse it with the solution it is to contain as to avoid changing concentration of that solution. Now how do we fill it? Is we're going to add a pipette filler. Why? Because solutions are toxic. So these solutions are very toxic, so you couldn't just suck on the pipette and the solution be drawn up, right? Just excuse us. So what happens then is we're going to draw up the solution. So we're going to rinse it with deionized water to clean it, rinse it with the solutions to contain to avoid, so exactly. So attach the pipette filler, draw up the solution until above the graduation mark, then place a waste beaker underneath the pipette and draw the solution out into the waste beaker until the bottom of the meniscus is on the graduation mark, read at eye level. And then when we empty the pipette, remember to touch the tip of the pipette against the inside walls of the conical flask. Okay, fine, we get that lingo. Then we have conical flask. We only rinse it with deionized water to clean it. Now, some precaution with the conical flask is when we're approaching the endpoint, let's say we can place the conical flask on a white tile to ensure that we can accurately see the color change. Another thing we can do is we can rinse the inside walls of the conical flask with deionized water to ensure all of the solution from the burette reacts with all of that solution in our conical flask or in our reaction vessel as it's called. And remember, another thing we can do is we can also swirl the contents of the conical flask. That's why it has a wide base but a narrow neck as well. So you can swirl it, yeah, without the solution going all over. So how do we do this? So graduation mark, this is all bullshit. Okay, that's fine. Swirl continuously. Wash down with deionized water. So we talked about all of these different things, right? And then yeah, I'll show you exactly why I would do it. So what indicator did we use? Yeah. So I know it's methyl orange. Now methyl orange in acidic conditions is going to be red. In basic conditions or alkaline conditions, it's going to be yellow. Yeah, I believe. So let's just double check that. Conical flask turned pink. So yeah, methyl orange is yellow in alkaline solution. Over here it's saying yellow to pink. I will go with yellow to pink, right? So we'll say, okay, yani yellow is so yellow is alkaline, and I'll say, okay, pink is acidic. Yeah, it makes sense. Like, pink, but then for phenolphthalein, pink is alkaline and colorless is acidic. Just keep that in mind. It's different. So let's just do an exam paper. Let's just do a few exam papers on this. Yeah, just quickly. I'll be honest with you. Yeah, the leaving cert is piss, man. Like we're so privileged, and like we take this for granted, bro. But it's genuinely piss. So don't fear, bro. I got your back. Alright. So basically what it's saying is identify a primary standard that could have been used. Remember we said what a primary standard was. A solution. A primary standard is a solute. It can be made up to a standard solution. It's 100% pure, stable in air, high molar mass, and readily soluble in H2O. In that case, in 2020 question 1, our answer is going to be anhydrous sodium carbonate. Yeah, so anhydrous sodium carbonate. This one's likely for this year, so anhydrous sodium carbonate. Yeah, so now we have B. So we're just going to write some bullet points, right? So now it's already, so tip contents of clock glass into beaker, rinse clock glass with deionized water, and then what we're going to do is we're going to pour rinsings into beaker, stir contents of beaker using a clean dry glass rod. using a clean dry glass rod, right? Then add funnel, ensures all solute dissolves, add funnel to this is a long process. But I'm not giving up a fight this easily, man. This is not who I am. This does not run in my blood. So pour rinsings into volumetric flask. I'm kind of abbreviating now. I wouldn't do that in an example. Oh. Then, okay, so that's part B done. Now part C is telling us, okay, name a suitable indicator. We know it's methyl orange. I'm praying that this is the one for our year. I think it will be, but you never know, man. They can pull a fast one on us, bro. Like this, like this. Alright. So what's our color change? Justified choice. It's a strong acid, weak base titration. Strong acid. We know that HCl is a strong acid. It's a monobasic acid because all molecules dissociate in solution, and it's a good proton. It's a good proton donor, according to Bronsted-Lowry. Yeah. So strong acid, weak base titration. The next question is going to throw you off, yeah? So first of all, we have to determine what's in the burette and what's in the pipette in order to tell what the color change is going to be. Color change, not color change. See, language is key, yeah? So, I mean, what's going on? So we're going to see which one we have been given the average titer for. So 21.5 centimeters cubed, that's kind of like an average titer, right? So that means HCl has to be in the burette. So the HCl has to be in the burette. And that automatically puts our anhydrous sodium carbonate, which is our standard solution, into our primary standards. Yeah, so it puts it here into our conical flask. That means we're going from alkaline to acidic, so we're going yellow to pink. Wow. Now we're just going to take this, and it says on average. So now I'm going to show you exactly how I do it. So I take a burette, right? And then I take a conical flask. Yeah, I'll take a conical flask. Okay, fine. I'm going to do volume, moles, and N. Volume, moles, and N. The beautiful thing is, we just determined that the HCl is here and the Na2CO3 is here, right? So what is my volume? It's just 21.5 centimeters cubed. It's 0.212 molar, and the moles is 1. But the moles here is, no, sorry, the molar ratio is 2:1. So 2 of these. Oh, I put them in the wrong place. No. It's fine. Good. 21.5 centimeters. This just proves that under pressure, yeah, you can do stupid things in your life, bro. Alright. So this is conical flask is usually because they use a bulb pipette. Bulb pipette is usually around 25 centimeters cubed. Alright. So let's say I take my volume, right? My volume is 25 centimeters cubed, yeah, and my molarity I don't know. I don't know. It's a question mark. It's a question mark, yeah? So what I'm going to do is I'm going to use the molar ratio. I'm going to use everything to start answering these questions. Nowadays, they ask it step by step by step by step rather than getting straight to the answer. So the average number of moles of HCl used up in the titration. First of all, we have to find the moles of HCl. Exactly. So we have 0.12 in 1,000. So we divide this by 1,000 and we'll multiply this by 21.5. So 0.12 over 1,000. And then we multiply by 21.5. So that gives us 2.58 by 10 to the minus 3 moles, which could be found in 21.5 centimeters cubed. HCl, we know it's HCl. Okay, the number of moles of Na2CO3. So we use that molar ratio. So 2 is to 1. So we have 2.58 by 10 to the minus 3. So here we're just going to divide by 2. So divide by 2. 1.29 by 10 to the minus 3 moles. But yani, look, it's in 25 centimeters cubed. The cheeky bastards, they did that again. Alright, so then what's the next question? They said the number of moles of Na2CO3. Beautiful. All you have to do is multiply by 10. And now we have 0.0129 in 250 centimeter cube. You wonder why they say 250 centimeter cube? Because that's the volume of the volumetric flask. Okay, alright. Now the mass. Now the mass of sodium carbonate, I believe, is 106. But I know. Bro, I kind of know, like 23 plus 12 is 58. 58 plus 48 is 106. Yeah, 106. So if I just multiply this by 106, multiply by 106, it gives me 1.3674 grams in. Now here's where it gets interesting, cuzzy, because they're really going to start trolling, yeah? So this is how much sodium carbonate I have. Now the mass of water crystallization, and hence the number of moles of water. The mass of the water of crystallization. Now if my crystals in total, with the water, and the sodium carbonate is 3.46, I'm just going to do, but that's in how much? In 250 centimeters cube. So this is 250 centimeters cubes, this is 250 centimeters cube, so it matches up. Beautiful. So I'm just going to minus that, like 3674, and I get 3.46, 1.3674. Okay, so I get 2.0926 grams. But keep in mind now, guys, the beauty of this is that this isn't water. This is water. So how do you find the number of moles? You divide by the relative molecular mass of water, which is just 18, because 16 plus 2, 18. So you divide by 18. That gives you 0.116255556. I don't know, I just have a habit of writing down all the moles, right? Moles in 250 centimeter cube, yeah? And it said, hence, find the ratio, right? So VR. Helps find the ratio of moles of water crystallization to moles of sodium carbonate. Moles of water. So we just put this number here, and we're going to divide by the smallest number. This actually makes so much more sense now that I'm doing it now, because I'm doing it using my brain this time around. Unfortunately, some other times I did not use that, but 0.0129, 0.0129 divided by 0.0129. Yeah, so I got 9 is to 1. So x is equal to 9. Alright. Percentage water crystallization would just be like 1 point. So it would just literally be just 2.0926 all over 3.46 multiplied by 100. That's it. You can do the moles, you can do the grams, whatever you want. I'm just going to do this just for this question. 3.46 multiplied by 100. Yeah, so 60.47%, yeah? Even if you do the moles, yani, you can do that as well. So you can do like 0.0129 percentage water of crystal. No, you'd use the grams. Yeah, I don't think you'd go into the whole complexities of everything. But yeah, so that's that. So that titration is done. So that was a hard one. Alright, so next one is vinegar, right? So we want the concentration. How do you want? We want percentage weight per volume, which means the number of grams in 100 centimeters cube. But I feel like I've done this. I've been there, done that, bro. Come on, ethanoic acid. So weak acid, ethanoic acid. Remember, it's a weak acid. All organic acids are weak because they're poor proton donors. And not all molecules dissociate in solution. Keep that in mind. So vinegars by titration against standard sodium hydroxide solution. Standard means it's a solution of a known concentration, yeah? Weak acid, strong base. So think about that. Weak acid, strong base, we're going to use phenolphthalein. Because if we look at our graph, right, the vertical rise or the vertical drop between the lines that we've drawn coincides with, it's going to be pH 8 to 10, yeah, for phenolphthalein. Yeah, keep that in mind. So if we come here, we have sodium hydroxide, this is the one where we have to use dilution factor, yeah, and we have to multiply by that as well, because it's dilute, because phenolphthalein is colorless and acid. Yeah, remember I said. Remember, this is cheeky. This is very cheeky because it's yellow. It's pink in acidic in methyl orange, but it's pink in alkaline in phenolphthalein. Phenolphthalein or whatever. Yeah. So dry concave flask. Blah 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 whatever. Blah, 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 blah. All right. Let's just do an exam paper question because you learn more from exam paper questions. And plus, I've done this before. 10 million times in my life. All right, so it says name the piece of apparatus used to measure accurately the 10 centimeter. Okay. All right, I'll say, what do you say? Burette, pipette, yeah, okay, exactly. You can use whatever you want. Yalla. Okay, that's good. All right, let's go. All right, so this first piece of apparatus, I'm gonna go for burette, right? Now, how do I describe? How do I clean it? How do I clean? Yeah. All right. So how do I clean it? So rinse. Remember we said rinse with deionized water to clean it. Rinse with solution is to contain. So what's the solution is to contain? Rinse with original vinegar solution. Solution to prevent changing its. We're gonna do every single exam paper, but I don't care. Whatever you think, whatever you say, we're getting this done, bro. So how are we gonna dilute this up, right? So the way I would dilute it is, oh sorry, not burette. I'm gonna go with pipette, just so that it goes right. So I'm going to draw out. So we're gonna draw out a solution. We're gonna draw out original vinegar solution from pipette, yeah, into 50 centimeter cubed what is it called, volumetric flask, ensuring to touch tip of pipette against wall of flask. Add deionized water until 1 centimeter below graduation mark. Then add dropwise until bottom of yeah. calculate. Okay, okay. Okay. So now we need to find the dilution factor. So dilution factor is equal to 50 over 10, which is equal to 5. So we have to multiply anything by 5. Okay. Now, okay. Aki. Calculate the volume of undiluted vinegar, which could be required to neutralize 25 centimeters cubed of the. Okay. So let's do this. Come on. Alright, so we're gonna have to determine exactly what's in the pipette, what's in the burette. Okay. So on average, so my dilute vinegar is here. Yeah, that means that my sodium hydroxide is here. Yeah, sodium hydroxide is a base. Dilute vinegar, sodium hydroxide. How do I go about this? What am I going to do? Is I have my dilute vinegar, I have my sodium hydroxide. I'm going to go vol n, and I'll go mol n. I'll go vol mol n. Yeah. So my volume, yani, was 12. Oh, sorry, I don't know, my connection kind of ended. Okay, all right. So I said my volume was 12.4. I said my moles was I don't know. Okay. And I said that the vinegar was, it's a 1:1 ratio. Sodium hydroxide was 25 centimeters cube, and the moles was 0.09. So it says calculate the volume of undiluted vinegar, which would be required to neutralize the 25 centimeters cube of. Okay, so now first of all, I have to calculate the moles of the normal vinegar. So if I have 0.09 divided by 1,000 multiplied by 25. Sometimes in chemistry, bro, yeah, you just kind of have to play around with the numbers, and eventually something just like kind of clicks. So 0.09 divided by 1,000 multiplied by 25 is equal to 2.25 by 10 to the minus 3. Now it's a 1:1, so this is 2 and 12.4 centimeters cubed of diluted. So we're going to have to multiply everything by 5. What about 12.4 divided by 5? 2.48 centimeters cubed. I think that's the answer. Let me just check it. 2.48, yeah. Exactly, yeah. Now it says outline an advantage. I think an advantage would not require excess amounts of. So why do you want to do this? Would not require excess amounts of sodium hydroxide. Would not require an excessive amount of sodium hydroxide to neutralize the undiluted vinegar. Outline an advantage of diluted vinegar before carrying out the titration. Smaller percentage air, more accurate, and less concentrate, less NaOH. So, less concentrated sodium hydroxide. So we'd have to use less concentrated, smaller percentage air. Smaller percentage air seems to be like one that you can always run, and a more accurate volume. So you see, less concentrated sodium hydroxide, that's the best answer. Less concentrated sodium hydroxide would be needed. Because if you have more concentrated sodium hydroxide, it might be more expensive, it might be more dangerous on the skin, it might be corrosive. So yeah, that's why we don't want that. So smaller percentage air, also more accurate volume, whatever you want to put down, right? Now it says state the color change observed at the endpoint. So we know that we're going from acid, with vinegars and acid because it's ethanoic acid. We're going from basic to acid solution. We're going from base to acid. Now phenolphthalein indicator, so that's going to be pink to colorless. Because if we look back to electrolysis, we know the hydroxide ions are going to build up around the cathode. And and phenolphthalein is when we're using that aqueous sodium sulfate solution, I think it was. Yeah, no. No, it's the one where we're doing the aqueous potassium iodide, yeah, with the inert electrodes and the phenolphthalein indicator. Pink to colorless, yeah? So now let's do this. Let's do this titration. So it says calculate the number of moles of sodium hydroxide in each 25 centimeter cube portion. Yeah, so we did this already. So it's 2.25 by 10 to the minus 3 moles in 25 centimeters cube. Part 2, it said calculate the number of moles of ethanoic acid in each centimeter cubed of the dilute vinegar. So it is 2.25 by 10 to the minus 3 moles in 12.4 centimeter cube, because there's a ratio of 1:1. Then I just divide this by 12.4, so it's equal to, so I have 2.25 by 10 to the minus 3. But I'm telling you, don't stress. Trust the one above, bro. And you'll make it, bro. You'll make it in life, cuz. Don't stress out too much, man. Life's temporary, bro. That's what I always say. Yeah. This says calculate the concentration of ethanoic acid. So first of all, I just want to make sure that's correct. Yeah, beautiful. It's correct. So calculate the concentration of ethanoic acid in the original vinegar in moles per liter. So this mole per centimeter cubed. Now if I multiply this, so it's part 3, is I just multiply that by 1,000 to get, yeah, right? So I just multiply by 1,000 and I get 0.181 molar. Now calculate concentration of ethanoic acid in, it's molar, but I multiply that by 5. Multiply by 5 is equal to 0.907 molar. Is 0.907? Yeah, 0.907 molar, yeah. And then last but not least, now we got it back into the concentrated one. So all we need to do is divide by 10 to get into 100. So divide by 0.907 divided by 10 is equal to 0.0907 moles in what we would call 100 centimeters cube. So then if I multiply that by ethanoic acid, which is like 12 plus 3 CH3 COH, yeah, so I have CH3 COOH multiplied by 0.0907 is equal to 5.442 percent weight per volume. That's beautiful. So we know this titration as well. I'll do more exam questions once I've completed all of them. But okay. So if the note 1 here. Oh yeah. So the vinegar. Why was the vinegar diluted? The vinegar was diluted. Why was the vinegar diluted? The vinegar was too concentrated and would require an excess amount of sodium hydroxide to react with. So basically, vinegar too concentrated. That's what I say. Would require excess amount of NaOH to react with. Yeah, so it's too concentrated, require an excess amount of sodium hydroxide to react with it. That's fine. Khalas, done. Okay, let's move on. Let's go. Okay, quick. Okay. Now we have potassium manganate. Okay. So we have standardization to find the concentration of a solution by colorimetry. Remember, the principle of colorimetry is that the concentration of solution is proportional to the intensity of the color. And then titration, this is what we're doing right now. So standardization of potassium manganate, so KMNO4, which is a secondary standard, which means it's a solute that cannot be made up to a standard solution, not 100% pure, not stable in air, not low molar mass, not readily soluble in H2O. So that's all the properties. You have to know that. You have to know that. So what we're going to do is, this is a secondary standard. Yep. And then we're using ammonium, iron 2 sulfate, ammonium iron 2 sulfate crystals. Sorry. Ammonium iron 2 sulfate, which is our primary standard. Ammonium iron 2 sulfate is a primary standard, yeah? So, but okay, whatever, right? So what do we add in order to prevent the aerial oxidation of iron 2 to iron 3? Because iron 2 plus likes to get oxidized iron 3 plus. Oxidation is loss, oil rig. So loss of electron. So it likes to lose an electron to become iron 3. So how do we keep it at iron 2? Sulfuric acid is added to prevent the aerial oxidation of Fe2 plus Fe3 plus. Sulfuric acid is added when preparing the ammonium iron 2 sulfate solution. Ammonium iron 2 sulfate solution prevents the aerial oxidation of iron 2 plus to iron 3 plus. So it's used to prevent. So ammonium iron 2 sulfate is used to prevent this. Okay, whatever. So during the inacidic conditions, so titration are required in acidic conditions to ensure that the complete reduction of Mn plus 7 to Mn plus 2. So Mn plus 7 to Mn plus 2 is going to be purple to colorless. So Mn plus 2 is colorless, Mn plus 7 is purple. But Mn plus 4 is a brown precipitate, which could form if there's not enough. If it's so look, if there's insufficient acid, a brown precipitate of MnO2 to rectify, we just add more sulfuric acid to the conical flask. Yeah? You ready? Let's do it. Let's do it, Ak. This is easy, bro. Like, why was I stressing out, man? So they didn't, okay, yeah. Alright, we'll do 2023 question, yeah? Alright. So it says, describe how you would prepare 250 centimeter cubes of standard solution containing this class. So let's just do this verbally. So state two properties of the substance that make it suitable as a primary standard. We can give all of them. Can be made up to a standard solution, 100% pure, stable in air, high molar mass, readily soluble in H2O. Done. We give 5. You only need 2. Now, how would you do this? Tip the contents of the clock glass into a beaker, rinse the clock glass with deionized water, pour the rinsings into the beaker. Now, get a clean, dry glass rod, stir the contents of the beaker until all the solute is dissolved. Now, add a funnel to a volumetric flask, pour the contents of the beaker into the volumetric flask. Remove the funnel. Now rinse the funnel, the glass rod, and the beaker with deionized water. Pour the rinsings into the volumetric flask. Now add deionized water to the volumetric flask to 1 centimeter below the graduation mark. Then add dropwise until the bottom of the meniscus is on the graduation mark. Read at eye level. Stop and invert 20 to 30 times to ensure uniform concentration. Done. Dusted. Light. Alright. What was dilute sulfuric acid adding during the preparation of this standard solution? To prevent the aerial oxidation of Fe2 plus 2 Fe3 plus in ammonium iron 2 sulfate. Now, how is the endpoint of each titration detected? I mean, when solution in conical flask, when a solution in conical flask turned colorless, yeah, and then brown precipitate as Mn plus 7 was reduced to Mn plus 4 instead of mn plus 2. So I just want to just check something. Oh, failed permanent pink. Oh shit. That is, I'm stupid because I didn't see which one's in the. Okay. Chill out. Before we answer this question, let's just quickly do this. But this is the stupidity that can loot your H1, yeah? So let's just do this quickly. 2024 KMNO4. So KMNO4 is here. KMNO4. Yeah? Yeah. Okay. Yeah, because if KMNO4 is here, it's going to go colorless. When a permanent pale pink color remained, when a permanent pale pink color remained in the conical flask. Yani light. Okay, KMNO4, and then in here I have my I have my, oh my god, that's a fat equation. Alright, I'll write it all out for you. So 2SO4, FeSO4, so iron 2 sulfate, okay, and then 6H2Os as well, yeah. Because it's crystals, yeah. So you have to have that. Remember that you have to calculate X in the anhydrous sodium carbon and percentage water of crystallization, all that. Anyways, so we have vol mol n. We have vol mol n, and then we'll do the ammonium iron 2 sulfate solution. Yeah. So vol is the volume of this. It was 22.6, and then it was these cheeky bastards. You know what they did for the concentration? It's in grams per 250 centimeter cube. That's the trick. Some people wouldn't clock that. If you don't know, you don't know, which is annoying. But that's why you have to do the work. That's why you have to do the due diligence. So moles, we don't know. This is probably gonna be 25. Yeah, it's 25. So, these calculated. Okay, concentration of any moles per liter. Okay, we can do that. So first of all, we need to figure out this. Oh, no. That's wrong. This we don't know the concentration because this is our secondary standard. This is our primary standard. This is 9.31 in 250 centimeter cube. That means that if 9.31, yani 9.31 was, then divide. First of all, we have to find the concentration actually in 25 centimeter cube. So if I divide it by 10 is equal to 9.31 divided by 10, which means I have a 0.931 gram in 25 centimeter cubed. Then I have to somehow find the molar mass of this. So 14. No, sorry. So let's do it. 28 plus 8 plus 32 plus 64 plus 56, I think, plus 32 plus 64 plus, if you're asking how do I know this, too much past papers, bro. So 20, I recognize the number as well. 64 plus 56 plus 32 plus 64 plus 12 plus 96, 392, yeah. So 0.3 divided by 392 is equal to 2.375 by 10 to the minus 3 moles in 25 centimeter cube. Now if I divide this by 25 and I multiply by 1000, hopefully should get a beautiful answer of 0.095. Oh, it's right. Damn. The number of moles of Fe in a 25 centimeter cube portion of the standard solution. 2.375 by 10 to the minus 3 moles in 25 centimeters cubed. That was kind of pointless. Alright, okay, then it says the number of moles of potassium manganate 7 reduced to Mn plus 2 by this quantity. So, you have 5:1 ratio. So we have 2.375 by 10 to the minus 3. And we need to get this into 1. So we're going to just divide this by 5. So 2.375 by 10 to the minus 3. Okay, yeah, well, cool, good, well, whatever. And then 4.75 by 10 to the minus 4. But this is in 22.6 centimeters cubed. Yeah. The concentration of potassium manganese the moles per liter. Okay, okay. Divide by 22.6 and multiply by 1,000, and this by 4, whatever. So I divide by 22.6 and I multiply by 1,000, and I should get 0.021. Should be right. Yeah, that's right. Cool, whatever. I'm back. So what's the next titration? It's to do with the iron tablets, yeah? Let's do iron tablets. Let's do iron tablets. So percentage. Do we need to do pestle and mortar? Aye. Let's do it. 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 Iron to sulfur. Okay. So we're doing 2025 question 1. This one is the most least likely to come up, but they can still ask it. You know, they have a mind of their own. To be honest, it's not a standard exam. You get me, but they really have a mind of their own. They like to play with their own rules. We have to play by that. So first of all, it says identify a standard solution, a primary standard. So first of all, the one that we looked at, ammonium, iron 2 sulfate. That's it. I. Let's do it. Then it says B. Then it says outline the correct procedure for bringing the solution in the volumetric flask precisely to the 250 centimeters cube. So let's just look. A solution experiment to determine the iron 2 content of iron supplement tablets. The 6 iron tablets, total mass of 2.4896, were dissolved in dilute sulfuric acid. Fine, because we want to prevent the aerial oxidation of Fe2 plus to Fe3 plus. So the solution and the washing were transferred 250 centimeter cube volumetric flask made up to a mark using deionized water. So the transfer conical flask of fluoric acid. Okay, explain. Okay, so it says outline the correct procedure for bringing the solution in the volumetric flask to precisely the 250 centimeter. So I guess what you could do is you could add deionized water. So add deionized water to the volumetric flask until the until 1 centimeter below the graduation mark, then add dropwise till the bottom of the meniscus is on the graduation mark and read at eye level. Stopper and invert 20 to 30 times. This is an interesting question. They made it more harder. Drop by drop, and then meniscus on the mark. Explain why using more than one iron tablet in 250 centimeter cube increases the accuracy of the analysis, because larger values, smaller percentage error, larger concentration of iron, I'm guessing. A small percentage error, larger volume of high concentration of iron solution, 1 tablet error, smaller percentage error, basically, yeah? Smaller percentage error, because therefore, think about it. If you have a small potential error, if you're using more iron tablets, then you have to use more KMNO4. So larger volume of KMNO4. Use a high concentration of iron solution. So yeah, okay. Name the piece of apparatus used to accurately measure. Okay, pipette. Describe how this apparatus rinse. Rinse with deionized water to clean it. Rinse it with the iron 2 solution to prevent changing concentration of the iron 2 solution. Class. Explain why the addition of an indicator into a conical flask was not required. The reason is because the okay. Because the iron 2, because the KMNO4 acts as an indicator. I think that's what it is. I think it's, yeah, KMNO4 acts as the indicator. Potassium manganate 7 acts as the indicator. So let's just do that. T is that the potassium manganate um pale pink color in conical flask, brown precipitate as Mn plus 7 would be reduced to Mn plus 4 instead of Mn plus 2. Okay, now it says on average Hmm? Sorry. I just get stressed out. 22.5, 0.01 molar. Yeah, and it's 1, but it sounds 5. So concentration, we probably don't know. And then volume is 25. Yeah, we don't know the concentration. Actually, wait a second, we do, because the concentration would be. Wait, what is different? Calculate the number of moles of manganese. Calculate the number of iron. Okay. In 250 centimeter cube of the. Okay. So, yeah, we don't know. So, but just know that there was in here there was so there was grams was 2.496 and the volume was 250 centimeters cubed. Yeah. All right, nice. So then it says okay, pale pink. Yeah. So then it says calculate the number of moles of manganate 7 ions present in 20. Easy. So 0.01 you divide it by 1,000 and you multiply by 22.5. Simple. So 0.01, you divide that by 1,000 and you multiply by 22.5. You get 2.25 by 10 to the minus 4 moles in 22.5 centimeter cube. Alright, yeah. Number two. Calculate the number of moles of iron 2 present in 250 centimeters cube. So, first of all, 1:5 ratio, so 1:5, so swing that back, so 2.25 by 10 to the minus 4, we multiply that by 5, يعني we get 1.125 by 10 to the minus 3 moles, beautiful, and 25 centimeters cubed though, remember the volume changes, and then we need to find the number of moles in 250, so then we just multiply that by 10, multiply by 10, and then we get 0.01125 moles in 250 centimeters cubed. Bang. Okay, that says calculate the average mass of iron 2 in one tablet. So this is the. So let's find the iron 2 in all of the tablets. Yeah. And then we'll divide it by 6. So if I take 0.01125. And let's say I multiply this by 56. Multiply by 56. So this is 0.63 grams. Now if I divide this by 6, I should get 0.105 grams per tablet. We calculate the percentage of by mass. So if 6 of them were that, so 2.496 divided by 6 to get the number of iron in the grams of one tablet. So 2.496 divided by 6 gives us 0.416. Okay, beautiful. 0.105 on top of that, multiplied by 100 to get a percentage. So then we get 0.105. We put that over 0.416 and we multiply 100, and boom, we get 25.24%. And if it's wrong, you can change my name. And it's right. So yes. Alright. Mashallah. Okay, let's do this. Let's go to the next question. Alright, we're cracking this exam, bro. Like you see this. You know, I was procrastinating so much on this, but I feel so blessed to be able to do this right now, bro. Okay, so we have now sodium thiosulfate. I think I'm gonna get the whole chemistry course done today, right? Oh, man, my one weakness is feeling hungry, bro. But I think I would just push through iodine titration because there's nothing really memory intensive that I need to do next. Titrations. So we have sodium thiosulfate and iodine titrations. So the ones that were just the Winkler one, the sodium thiosulfate, the titrate. Okay. So sodium thiosulfate is a reducing agent. It reacts with iodine that has been liberated from solution containing excess potassium iodide. The secondary standard is not available in a pure state, and it goes into the burette. Now the I2 undergoes sublimation. Okay, it's important potassium. Why is it important that Ki is in excess? Why? Why do we want Ki in excess? To ensure the maximum amount of iodine is liberated. Number one, to ensure that all the oxidizing agent is reduced to the maximum amount of iodine is released due to the amount of oxidizing agent used, and to keep iodine in aqueous solution. So first of all, uh, uh, to ensure all of the oxidizing agent is reduced. So to ensure all of the to ensure all of the oxidation, to ensure all of the oxidizing agent is reduced, to release the maximum amount of iodine. So the maximum amount of iodine is liberated due to the amount of the oxidation. To ensure all of oxidizing, to ensure all of oxidizing agent gets reduced, uh, to ensure maximum amount of iodine gets liberated. So to ensure all the oxidizing agent, to ensure all of our oxidized agent, to ensure all of our oxidizing agent gets reduced, right? So the maximum amount of iodine is liberated due to the amount of oxidizing agent. So due to the amount of oxidizing agent. So oxidizing agent is sodium thiosulfate, and then to keep Ki in aqueous solution. Yeah. Okay. So basically, we're going to be going. Think about it. If I have iodine, I go from red brown. So I'm going to go. This is my color. So red brown to straw yellow. Then here I'm going to add starch. Then I go blue black, and then colorless. Bro, you see, I've been there. This is not my first rodeo. You get me? Alright. So let's just look at it. So let's try and find some of these cheeky. This is total hardness. Yeah, I think this is one, yeah. So it says, okay. So this is dissolved oxygen, right? Identify a compound usually added to the water to provide the MnO2. I think it's MnO2 or manganese dioxide, I believe it is. Explain why a large excess of Ki was required in synthesis to ensure all oxidizing agent is reduced to ensure maximum amount of Ki is liberated due to the amount of oxidizing agent. Okay. Now it says what, and then to keep Ki in aqueous solution. I guarantee you that's what it is. To liberate the maximum amount. Oh, it's not manganese dioxide. It's manganese to sulfate. That was a good catch. So MnSO4. Nice. Shows all oxygen is detected. Is kept in solution. Is it to keep iodine in aqueous solution? Yeah, shit. Oh, it's to keep iodine. So the two reasons I learned is that to ensure all of the oxidizing agent reduced to ensure the maximum amount of iodine is liberated due to the amount of oxidizing agent, and to keep iodine in aqueous solution. So potassium iodide is basically the closest we can get to keep iodine in aqueous solution. Now, another thing I want to just check here. It says, what change was observed when the concentration of sulfuric acid was mixed thoroughly with the contents of the sample bottle? Brown precipitate dissolved. So solution went from brown to colorless. Now describe how the conical flask was prepared for the titration and then used during the titration to help ensure the accurate endpoint was reached. So first of all, we're just only rinse the conical flask with deionized water to clean it. Then during the titration, we're going to swirl the conical flask. We're going to place the conical flask on the white tile to ensure that the color change can be accurately determined. And then also we're going to wash down the inside walls of the conical flask with deionized water to ensure all the solution from the burette is going to react with all the solution in the conical flask. Give one way of ensuring that the level of the liquid in the burette was at eye level. Um, to ensure that the bottom of the meniscus is on the graduation mark. Maybe that's what it is. Oh, use. Oh, place the burette on a lower surface. Place the burette on a lower surface so that it is at. So just place the burette on a lower surface. Okay. What color change were observed at titration? So up to the point when the indicator was added. So red, brown to straw yellow. And at the end point, it was going to be blue, black to colorless. Now, here we go. Okay. So I'm not perfect at this. I certainly am. Certainly am not. On average, 6 were required. Okay. On average, so this has to be our Na2S2O3 5H2O. Vol, mol, and yeah. Why do I just go like I don't seriously don't care about what they're yapping on about, bro. Like give me the details, bro. I'm done like this, bro. You get me? So then we had iodine solution. Apparently, iodine solution. Vol, mol, and N is 1. Volume of the iodine solution was 200 centimeters cubed, apparently. And the moles, we don't know. The average number of moles of sodium thiosulfate used in the titration. Can't lie, I'm not bothered though to rewrite this all out. I'm just gonna put this here, yeah. So average moles, yeah, is 3.1 divided by 1,000 multiplied by 6. 3.1 divided by 1,000 multiplied by 6, which is going to give us 0.0186 grams in 6 centimeters cubed. But then we need to multiply this by 2 by 23 plus 2 by 32. So sodium thiosulfate. So 2 by 32 S2O3, I think. Yeah. S2, Na2, S2O3 plus 48. So 46 plus 64 plus 48 no, sorry. 0 0.0186, sorry, 186 divided by 46 plus 64 plus 48. So I got 0.0001177 moles in 6 centimeters cubed. The number of moles of O2 that release the I2 detected in each titration. So I just need to divide this by 2. So you got 0.000058886 moles, right? But then what do we need to, sorry, this is part 1, this is part 2. So then what do we need to do? But it says for every, it says for every, it says for every 1 mole of this, for 4 moles of S2O3 were required. 4 moles of S2O3 oh, sorry. We don't divide it by 2. The number of O2 that released, the I2 detected in. So divided by 4, 0.0000147 moles. My back just feels so cooked, bro. I can't lie. Oh, bro. Alright, we're gonna have to redo all of this shit. I think I'm just gonna restart here. So, I'll just redraw the diagrams. I'll just redraw the diagrams. It's fine. It's fine. It's fine. It's fine. So let's just double check that we're doing everything correctly. So sodium thiosulfate solution contains 3.1 grams per liter on average. Okay. So this is sodium S2O3 5H2O. Yeah, yeah. And at the bottom, right, I have this I2 solution. So I have vol, mol, and N. And I have volume, molarity, and N. The moles, sorry, not molarity. Well, so this is 6. The moles of this is 3.1 grams per liter. And N for is 2. N is 1. Volume is 200 centimeters cubed. And moles we don't know. So this is what they're telling me. The average number of moles of sodium thiosulfate used in the titration. 3.1 grams divided by 46 plus 64 plus 48, which is plus 10 plus 80. 248. Divided by 248 in liter. So 3.1 divided by 248. So I have 0.0125 moles in 1 liter. Now if I divide this by 1,000 and I multiply by 6, I get 7.5 by yes, we got it. Alright, that's nice. So this is what we get in yani 6 centimeters cubed. Perfectly fine. All well and good. Now what it's saying is, this cheeky thing is saying, is for every 4 moles of S2O3 were required. So we're going to divide this by 4 basically, yeah? It's 1.875 by 10 to the minus 5 moles. It's actually 1.875. Yeah, it was, yeah. Okay, then it says the concentration of dissolved oxygen in the water in moles per liter. Divide by 6, multiply by 1,000. So got 3.125 by 10 to the minus 3 molar. Is that right? 3.125. Uh-huh. So it says the concentration of this. So we got the oxygen. This is the concentration of dissolved oxygen in the water in moles per liter. So why are we multiplying by 5 again? The concentration of dissolved oxygen. So yeah, I got the concentration, yeah? No, that's wrong. So 1.875 by 10 to the minus 5 moles. That's correct. That's correct. Now, the concentration of dissolved oxygen. How do I know it's moles per liter? What? So I have this. Oh, oxygen 200 centimeter cube. Why is it two? I don't get it. Wait, what? So yeah, 248 divided, get that, grand. This, I divide by 4, I get that, grand. This, okay, multiply by 5. So that's 200 centimeters cubed. Okay. Oh, so we use the iodine solutions 200 centimeters cubed. Ah. So, yeah. See, look, you learn something new every day. Like, that's the beauty of this, right? It's, remember, milligrams per liter, right? Multiplied by 32. So 3 by 10 to the minus 3 grams per liter. And then milligrams is going to be more, so it's 1,000. So I'm going to say 3 ppm. Divide by 32, no? Yeah. Oh no, no, no. I don't want. Change. Explain how iodine, a non-polar substance of very low water solubility, is brought into aqueous solution. Reaction with potassium iodide. Is this discussed in the... So by reacting a standard solution, so reacting standard solution standard solution of iodine. I just look at the marking scheme. Reaction with potassium iodide. Go on, man. Or just reaction with potassium iodide. Alright, that's good to know. So reaction with a potassium iodide. The iodine solution is made of 500 centimeter cube volumetric flask. Describe the procedure of measuring 25 centimeters cubed of this solution into a conical flask. So we're going to add a pipette filler to the pipette, right? Then we're going to place the tip of the pipette inside of the volumetric flask. We're going to draw the solution. We're going to draw the solution until above the graduation mark. Then we're going to place a waste beaker underneath the pipette, and we're going to draw the solution out into the waste beaker until the bottom of the meniscus is on the graduation mark and read at eye level. Then I touch the tip of the pipette against the inside wall of the conical flask, and I draw the solution slowly out into the conical flask. Name a suitable indicator for this titration. Indicator? Huh? KMNO4. Oh yeah, KMNO4. Potassium manganate. No, no, I'm getting mixed up. Sorry. Oh, starch, yeah. When the solution in the conical flask is straw yellow, at the point, state the color change at the end point. Oh, blue, black to colorless. Bro, I was completely got brain fart there, bro. Can't lie. Can't lie. So, D. D. So let's just go over this. Explain iodine is a reaction with potassium iodide. So it's brought into aqueous solution, reaction with potassium iodide. Made up to solution. Remember, pipette filler. So we take a pipette. Now, the pipette is rinsed with deionized water to clean it. It's rinsed with the iodine solution to prevent changing the concentration of the iodine solution. We then place the tip of the pipette inside of the volumetric flask, drop the solution to above the graduation mark, take the pipette out, place a waste beaker underneath the pipette, allow the solution out into the waste beaker until the bottom meniscus is on the graduation mark, read at eye level. Then touch the tip of the pipette against the inside wall of the conical flask and draw the solution slowly out into the conical flask. That's it. Now, name a suitable indicator, starch indicator. At what stage is it added? When the solution in the conical flask is straw yellow. State the color change, blue, black to colorless. Now, given that 6. Okay. You learn every day, bro. I have one more titration to do. No, two more. I have to do a bleach titration. I have to do an EDTA titration. So you see volume, yeah? It says 6.35 grams uh, of iodine in 500 centimeters cubed of the iodine solution. Yeah. So it says calculate the number of moles of iodine. So if I take 6.35, remember iodine is diatomic. That's why they put the cheeky I2 there, just to remind you that it is. Oh, my back hurts kind of. Oh, 127. Yeah. And that's in 500 centimeters cubed. Uh, I wanna thank. Okay, yeah. So yeah, that's basically that bang bang bang. 0.025 moles in 500 centimeter cubed, but they want to find in 25. So I divide this by 500, I multiply by 25. I divide this by 500, I multiply by 25, and I get 1.25 by 10 to the minus 3. 1.25 by 10 to the minus 3 moles in a 25 centimeter cube. The number of moles of sodium thiosulfate required to reduce. So we know that the ratio is 1:2. So it's just going to multiply by 2. So it's just 2.5 by 10 to the minus 3 moles. The concentration of the sodium thiosulfate in moles per liter is 17.85 centimeters cubed, of which were required to reduce 25. The concentration of the sodium thiosulfate solution in moles per liter, 17.85 centimeter cube, of which were required to reduce the concentration of the sodium thiosulfate solution in grams per liter. So 0.14 multiplied by 248, because I'm not bothered to do all of that, and then per liter. So 0.14 multiplied by 248 is equal to 34.72 grams per liter. Yeah. Distilled water versus deionized water, because so deionized water has no ions, but it has organic material and dissolved gases. And therefore, and then distilled water, it has no ions, no organic material, no dissolved gases. So therefore, there's nothing really in the distilled water is going to interfere. Just say deionized water has no ions, however, it still has organic material and dissolved gases, whereas distilled water has no ions, no organic material, and no dissolved gases. So that's it. That's it. That's it. That's it. That's it. That's it. Is there no like chlorine titration? Oh, I think this is the bleach one, yeah. Now it says a chemist determined the concentration of a bleach solution containing NaClO. So sodium hypochlorite by the volumetric analysis 25 centimeter cube. Okay. Describe a 25 centimeter cube sample of original bleach solution was diluted to exactly 500 centimeter cube. So draw up the original bleach solution into a pipette. Uh, oh yeah. Draw. So add a pipette filler to the pipette. Drop the solution, the original bleach solution, into the pipette and above the graduation mark. Place a waste beaker under the pipette and draw the solution out into the beaker until the bottom of the meniscus on the graduation mark read at eye level. Then we're going to place the tip of the pipette on the inside wall of the volumetric flask. Allow the solution out into the volumetric flask. Then we're going to add deionized water to the volumetric flask until 1 centimeter below the graduation mark. Then add drop ties till the bottom meniscus on the graduation mark and read at eye level. Stopper and invert 20 to 30 times to ensure uniform concentration. So yeah, exactly. What color developed when the potassium iodide and the sulfuric acid reacted with the dilute bleach in the conical flask? What color developed when the potassium iodide and the sulfuric acid reacted with the bleach in the conical flask? Straw yellow. Give 2 reasons why excess potassium iodide was used. To ensure all of the oxidized agent was reduced, to ensure the maximum amount of iodine was liberated due to the oxidizing agent present, and also to keep iodine in aqueous solution. Now, the solution of the conical flask. So, what was the purpose of the standing the conical flask on a white towel? To ensure that we can see the color change accurately. To ensure that we can see the color change of the color changes occurring in the conical flask accurately. Now, the solution, name the indicator, use starch, and at the endpoint is blue, black to colorless. Now, calculate concentration of NaClO and all that. So, let's do it. So we have this, volume concentration N, volume concentration N, bang, 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 bang. So what is in my, the average volume of sodium thiosulfate, so this is Na2CO3. I just like to write down the whole formula because sometimes what happens is you leave out the rest and then you don't realize that you miss out some of the mass and then the answer is wrong. So the volume was 16.1 centimeters cubed. It was 0.1 molar. And sodium thiosulfate was in a ratio of 2:1. Volume here, uh, 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 I'm guessing the concentration of the NaClO is the same as the concentration of the iodine. So let's just do that. So if I have 0.1, I divided by 16, sorry, I divided by 1,000 multiplied by 16.1. So I get 0.1 divided by 1,000 multiplied by 16.1. So I get 1.61 by 10 to the minus 3. Then I divide this by 2. So I get 8.05 by 10 to the minus 4 uh, uh, centimeters cubed in, okay, that's, no, sorry, not centimeters cubed, that's moles. That's moles. So at 0.1 moles, that's the number of moles but it's 2:1, so that's the number of moles, yeah? Then it said, calculate the concentration NaCl. Okay, so we need to get the dilution factor, which is 500 over 25. The diluted bleach was 8.05 by 10 to the minus 4 moles in 25 centimeter cubed. Now I need to divide this by 25 and multiply by 1,000. Yeah, so it's like 800 wait 8.05 by 10 to the minus 4, right? Now I divide by 25 and I multiply by 1,000. Yeah, so I get 0.0322 molar, and then dilution factor is 20, so multiply by 20, I get 0.644 molar. Now what was the concentration of NaClO in the original bleach in grams per liter? So if I have, let's say, NaClO, yani 35.5 plus 16 plus 23. So I have 35.5 plus 16 plus 23, which is equal to 74.5. Beautiful, no problem. Then I multiply that by 0.644, and then I divide that by 10, so I get 4.7978 grams. No, sorry. 8 grams. I multiply by 10, because, yeah. So, sorry. So then it would be 47.978 grams in a liter. And then if I then just divide it by 10, I get 4.7978 percentage weight per volume. I hope that's correct. Ah, lovely. We got it right. Nice, 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 nice. Now we're just gonna do one more titration, and then I'm gonna call it for today. All right. So identify the two ions represented by M2 plus, Ca2 plus, and Mg2 plus. Total hardness is permanent hardness plus temporary hardness. And then it's like suitable indicator is Ericom black tea. What color change were observed in the conical flask? So what's in the conical flask? In the conical flask and titration with standard EDTA. So so if we're going from red wine to blue, red wine to blue, if the EDTA is up there. Yeah, that's right. Now what pH buffer is pH buffer 10 solution? pH buffer 10 solution allows us to determine endpoint of titration more. Okay. Now, is that correct? Sharp, more accurate endpoint. Gives a sharp. Bro, I can't lie. I'm feeling kind of hungry, bro. Ethylene diamine tetracetic acid is a funny one. Volume concentration N. Volume concentration N. Bang, 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 bang. Now, okay, so EDTA. So we have So this is my hard, sorry, this is my hard water, and this is my EDTA. Yeah. So then I have numbers of moles. So I have basically volume is 9.2 centimeters cubed, 0.1 moles. So 1:1 ratio. So I have not. So I basically 0.1 divided by 1,000 multiplied by 9.2. So I have 0.1 divided by 1,000 multiplied by 9.2 is equal to 9.2 by 10 to the minus 4 moles in 9.2 centimeters cubed. Then that's part 1. Then part 2 is the number of, so M2 plus and H2. So the two ions, so the hard water is M2 plus, yeah? So magnesium or calcium, right? Number of moles of M2 that reacted with this quantity of EDTA. So 9.2 by 10 to, why did I clear my calculator? And then I just divide, no, it's the same. It's a 1:1 ratio. So 9.2 by 10 to the minus 4 moles. Now, the number of moles of M2 ion removed by the deionizer from a liter of original sweat. The number of moles of M2 plus ion removed by the deionizer from a liter of. Oh, so moles per liter. This was moles per 25 centimeter cubed. So you divide by 1,000. So sorry, divide by 25 multiplied by 1,000. Divide by 25 multiplied by 1,000. So 0.0368 molar. And the total hardness removed by the deionizer expressed in grams per liter of CaCO3. And then I multiplied this by CaCO3, which Ca has 40 plus 12 plus 48, so 100 multiplied by 0.0368, which is 3.68 يعني 3.68 grams per liter. So GL minus 1. So sorry. Yeah, so exactly. And then parts per million, which means 3.68 multiplied by 1,000, because milligrams is going to be more. 3680 parts per million. No shit, I think. So I'm in grams right now. If I want to go from grams to milligrams, I multiply by 1,000, no? Or maybe I did this part wrong as well. Oh. Oh, I messed something up. Okay, it's fine. Khalas, no problem. So if I have basically 0.1 divided by 1,000 multiplied by 9.2. The frick? And this is 0.1 molar. Oh, it's 0.0. Oh, 0.01. Divide, bro, this stupid mistakes can like get you as well, yeah? Wallah, man. Alright. Alright, khalas, we got that done. Alright. Alright. Alright, I think we're on the right path now. Divide by 25 multiplied by 1,000 gives us 3.68. 3.68 by 10 to the minus 3 molar, and then multiply by 1,000, and that should give me bro 9.2 by 10 to the minus 5. I divide by 25, I multiply by 1,000. 3.68 by 10 to the minus 3 molar. Now I multiply by 100 to get 0.368 grams per liter. And I multiply by 1,000 to get 368 parts per million. And that's titrations. Smack bam done. Which is a relief because I was procrastinating on it for ages. So that's basically the chemistry course done. I just need to do lab safety signs, test for anions, oxidation reduction, acids and bases, options, but I don't. Oh yeah, oh, that's grand. I'm kind of hungry now. I won't lie. I kind of need to sleep as well. So I appreciate you joining in. That's 1 hour 41. Uh, that was 1 hour 41, yeah, of deep work. You get me? We're going to be back here. Come on. We're going to be back here. يعني tomorrow, hopefully around maybe 8 a.m. Yeah, half 7, 8, probably 8 a.m. We'll be back, and we will try to just get the rest of the chemistry course done, and then we're going to start trooping through, uh, again, going through organic 5 through 10. So all the organic experiments, aldehydes, ketones, carboxylic acids, more in detail, the mechanisms for free radical substitution, so initiation, propagation, termination, then the 4 stages of free radical of ionic addition reactions for alkenes, and then heterolytic fission, homolytic fission, all that stuff. And like, yeah, we'll go through that. We'll go through the esterification reaction. We'll go through the um, glycerol tristearate and sodium stearate. So that's esterification. What other one was? Oh, the benzoic acid and then recrystallization as well. Um, what else was there? Yeah, I think there's quite a few experiments there to go through. But yeah, we'll get it all done, and then we'll do a bit of English as well. So, actually, just look in here. I'll look at English real quick, and we'll just see that English. Yani, we're going to be doing a few quotes. A few quotes. I'm going to do. That's not good. Why is there only? Why is there no quotes there? Oh, bro, this English shit is just getting worse and worse by the day, bro. Where's my quotes gone, man? Bro, I feel kind of screwed, bro. I feel so screwed. Um, hopefully we find it. Hopefully we find it. Hopefully we find it. English. No, 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 no. English, English, mock, English. Thing is, I should have been more organized in my notes, but I can't let my notes are all over the place. Swear down, bro. Ah, we found it. We found it. We found it. We found it. Oh my god. Oh my god. We found it. We found it. We found it. Yes, come on. Come on, G. So we don't need that. So now we just have. Huh? What? Where did... I'm just getting stressed out, bro. It's just raising my blood pressure. My blood pressure is already high, bro. This is it, yeah? So my MacBook code's here, and my comparative here, and then yeah. Okay, we're saved. Okay, bro, I was